So now today we discuss some special type of sets. So the first one is sometimes called empty or null set. Empty or null set. Now what is empty or null set? That is a set which contains no element, which contains no element. A set which contains no element is called empty or null set, or sometimes void set, and it is denoted by one is this symbol phi. This is the Greek letter phi, phi or phi, or even you just put such two curly braces. This is also symbol for empty set, this or this. For example, if I take let's take a equals to all x such that x is between 1 and 2 and x is an integer. Now you know that there is no integer between these two. Remember, you mentioned here integer. So this is an example of null set phi, a equals to phi. Or you can write a equals to like this, just put such two curly braces. One more, if I let's take b equals to all x for which x square plus 1 equals to 0. Now you know that there is no x for which x square plus 1 is 0. For any x, if I put here, and if I add 1, this never be 0. So this is also an example of null set. So B is null set phi. Okay. Now next type, which is Singleton set. Singleton set. That is a set having one element. Set consisting of exactly one element is called Singleton set. For example, let's take a equals to this. This is read as Singleton 1. If I write b equals to this, Singleton alpha. If I write c equals to, let's write small a, so this is Singleton set. If I write d equals to this, remember now this is not Singleton set. Within the set you have an object. Here object is this phi. So this is also Singleton set. This is not empty set. If I write like this, which is empty, but within these two braces I have placed some object. So this is a Singleton set. Set consisting of exactly one member. Now next, which is finite and infinite. Finite and infinite sets. Now what is the finite set? That is a set consisting of some fixed number of elements, Finite does not mean small set, remember. It should have some countable number of elements. If you can count the elements of a set, then it is called finite. It should end somewhere. And a set which is not finite is called infinite. is called infinite. That is endless, it never ends. Like set of natural numbers, it is an infinite set. Right? You cannot count all members of the set, which is called infinite set. A set which ends somewhere, that is, that has some fixed number of elements, that's called finite set. A set consists of fixed number of elements is called finite set. Is called finite set here. Here, set which is not finite is called infinite set. For example, if I take A equals to this 1, 2, 3, and so on up to 100, so this is a finite set. If I take B equals to this, for example, 2, 4, 6, 8, up to 1000, so this is a finite set. If I take C equals to population of Ahmedabad city, population of Ahmedabad city, this is also finite set. So these three sets are finite. You can count the population of Ahmedabad city. So these are the finite sets. Now next, if I take set of natural numbers 1, 2, 3, 4, now this is endless, it never ends, so this is an infinite set. If I take this as a standard symbol, n equals to this is an infinite set. This is an infinite set. It never ends, natural numbers is countable, but you cannot list all natural numbers. Usually in infinite set we write 3, 4 members and then we put dot dot dot. Okay. Now I'll list some standard infinite sets of numbers. The one is n, natural numbers, capital N, which is 1, 2, 3, 4 and so on, positive integers. Set of positive integers, this is called set of natural numbers also. The next one that is Z, all integers, 0, 1, 2, 3. On the other side you have -1, -2 and so on. Set of all integers. All integers means positive integers, negative integers and 0. Here you have just natural numbers, which is positive integers. The next we have third one, which is Q. This is called set of rational numbers. Numbers of this type, P by Q, such that where P is an integer, belongs to Z, Q is also an integer, but Q should not be 0 because you are writing in denominator. Right? So this is set of rational numbers. Set of rational numbers. Rational numbers means numbers which are in this form, one integer upon the other integers. So for example, 2 by 3, 4 by 2, 7 by 4, -1 by 2, -4 by 6. Then if I write just 4, if I write 100, you can imagine 100 by 1, 4 by 1. All are nothing but rationals. These are called rational numbers. Rational numbers. Numbers which are not rationals are called irrationals. Are called irrationals. For example, root 2, root 3, root 5, pi. These all are irrational numbers. So these numbers cannot be expressed in this p by q form. You also know that if I pick up any number, then either it is a rational or irrational. So finally, fourth largest set, that is R, which is called set of real numbers. Set of real numbers. So every real number is either rational or irrational. If I pick up any real number, then it would be either in p by q form or it is not in p by q form, that is a rational number. So these are the four standard sets on numbers which are infinite. So this n, z, q and r. These are infinite sets of numbers, remember, which we use frequently. So this n, z, q are very standard notation. N, then z, then q, then r. In your textbook, these are used as bold letters. N, z, q, r. I repeat, n means all natural numbers, positive integers. Z means all integers. Q means rationals. And r means all real numbers. Every real number is either rational or irrational. One more definition here before we go to the next exercise, that is about equal sets. So the question is, when two sets are said to be equal, two sets A and B are called equal if they have exactly same members. Such sets are said to be equal, and we write A equals to B if they are equal. This is the symbol. For example, I'll write A equals to this set. Let me write x such that, for example, x square equals to 1. And if I write b equals to, I'll write this minus 1 and 1. So then clearly A equals to B. Why? Because there are two numbers whose square is 1. So if I list the members of this set A, then again we'll get the minus 1 and 1, and which is B. So therefore we write A equals to B. Okay, so let's see next exercise 1.2. The question is, which of the following are examples of null set? So first question is set of odd natural numbers divisible by 2. Now odd numbers, 1, 3, 5 and so on. They never divisible by 2. So this is an example of null set. You can denote it by that Greek letter phi also. Okay. Set of even prime numbers. Prime starts from 2, then 3, then 5 and so on. So which is the even prime number? 2. So this is not a null set. This is not a null set. In fact, it is a singleton set. Set. You can write if you want. In a set, you have this 2, and then I'll complete the curly braces. Singleton set 2. So this is not a null set. Third question, x, where x is a natural number, less than 5, and x should be more than 7. Now less than 5 means 4, 3 and so on, and more than 7 means 8 and so on. So this is again null set, because we don't have any natural number that satisfy this condition. So no x will be member of this set, so null set. Next question, which of the following sets are finite or infinite? You know, finite set means what? It should have fixed number of elements. Set of months in a year, you know, 12 months in a year. So this is a finite set. This is here a finite set. Finite set because you can count the members, which is 12. The next example is 1, 2, 3 and so on. Dot dot, this 3 dots indicates that it goes on, never ends. So this is an infinite set. Infinite set. It never ends. Next, obviously 1, 2, 3, 99, 100. So it has fixed number of elements here, which is 100. So this is an example of a finite set. This is a finite set. Next, set of positive integers greater than 100. Positive integers greater than 100. Now what do you think for this? This is obviously infinite set. This is infinite set because this never ends. Infinite set. In a set, if you want to write, you can write here in a set 101, then 102, then 103 and so on. So this never ends, goes on. So this is an example of a set of all positive integers greater than 100, 101, 102. This is an infinite set. Okay, so here next question is fifth one. Are the following pairs of sets equal? That's a question. Now here set A is this 2, 3. The other set B is x, where x is a solution of this quadratic equation. So you can factorize this quadratic equation and you will see that the factors are this here: x plus 2 into x plus 3, that you know from 10th standard equals to 0. So here what are the possible values of x? That is x equals to -2 and -3. These are the values. So members of B are these two, -2 and -3. So B consisting of these two members. So B equals to, here in a set you have these two members, -2 and -3. So clearly here A is 2, 3, B is -2, 3. So therefore A and B are not equal sets. Okay, second example, set A, that is x is a letter in this word. So what are the members of this? Here members of these are F, then O, then L. Now there is again L, but we cannot repeat, and finally last W. So these are the 4 letters without repetition, you know. Next question is here B equals to, Y is a letter in this word. So what are the members here? W, then next O, next L, and next F. So here this set also consisting of these 4 members: W, O, L and F, and you know that these two are equal. So here you can say that A equals to B. These two sets are equal. Okay. Now next important concept is about subsets. So we take two sets, take sets say A and B. So we say that A is a subset of B. We say that A is a subset of B we say that A is a subset of B if every member of A is also present in B. If every member of A is also present in B, then we say that A is a subset of B. And we write symbolically by this symbol A, then this sign, and then B. This is read as A is a subset of B. And in this case, we say that B is called superset. B is called superset of A. Superset of A. So in the sense that the B is a bigger set and A is a smaller set. Like this, for example, let's take A equals to 1, 2, 3, and I'll take B equals to, for example, 1, 2, 3, 4, 5. I'll take C equals to, for example, let me take 2, 3, 4. So about these three sets, every member of A is in B. 1 is here, 2 is here, and 3 is here. So we say that A is a subset of B. Now, every member of B is not in A, so B is not a subset of A. B is not a subset of A. 2 is in B, 3 is in B, and 4 is in B. So we say that the C is a subset of B. Now, 1 is here present, but 1 is not present here. So therefore, you can say that A is not a subset of C. 4 is present here, but 4 is not present in this. So C is not a subset of A. So this way we write the subset and not a subset relation. Now we write this important remark here. One is null set. It consisting of no member. So we say that null set is a subset of any set A, where A is any set. Null set or phi is subset of every set A. And secondly, every set is always subset of itself. These are the two important things about subset. It's like our number system, if you recall. If I take any number, for example 2, then it has two divisors, minimum two divisors. One is 1 is divisor of every number, the other one is 2. So every number has at least two divisors. One is 1 and the other one is itself. If I take 10, then it has number of divisors, but which are minimum two divisors. That is, one is 1 is divisor of 10, the other one is itself. It has 2, 5, and so on. But every number has at least two divisors. One is 1 and the other one is itself. Same way here, every set A has at least two subsets. One is phi and the other one is itself. So this we need to remember. If you are given any set A, then it has at least two divisors. One is phi. Phi is a subset of every set A, and the other one is always subset of itself. Now here, if A is a subset of B, that is, every member of A is a member of B, and B is also subset of A, that is, every member of B is also member of A. If this happens, then sets are equal. And we write A equals to B. So here, this is very important point. Two sets are equal. This is read as double implies, in fact, sorry. Two sets are equal if and only if double implies one set is a subset of the other one, and reverse, the other set is a subset of the first one. Right? This is always true. This is very important remark. I repeat, two sets are equal. It implies A is a subset of B, and comma means and B is a subset of A. And conversely, if for two sets A is a subset of B and B is a subset of A, then those two sets must be equal. This is a double implies. So this we use even in examples also. So this we use later on. Like in this example, if you see here, A is a subset of B, but B is not a subset of A. So these two sets are not equal. A is not equals to B. A is a subset of C, but A is not a subset of C. So obviously A and C are not equal. So this way we use this concept of equality. Now next important definition is about power set. Power set of a set. So we take a set here for a given set A. For a given set A, a set of all, remember again you are forming a set of all subsets for a given set A set of all subsets of A is called power set of A, and we write so here P of A, it's a symbol for power set of A. Don't get confused with probability of A, remember. So I repeat, what is power set? You take a set and then you list all subsets of a given set A. That's called the power set. So here members of the power sets are all subsets of a given set. For example, I'll take A equals to Singleton 1. Now what are the subsets of this? So here subsets 1 is Null Set. You know it is a subset of every set. And the other one is Singleton 1, which is A itself. So these are all subsets of A. Therefore what is P of A? A set means within this curly brackets you put these members, that is 5 and A. So this is a power set of A. If I take next B equals to, suppose B equals to set having these two members A and B. Now what are the subsets here? So subsets 1 is Null Set. It is a subset of every set, you know. Then I'll take one set consisting of single member, Singleton A, it is a subset of B. Then Singleton B, it is a subset of this. And then AB here, which is B itself. You cannot take BA, you know, AB and BA both are same. So what are the subsets of set B? Phi, Singleton A, Singleton B and B. So what's the power set of B, which has these four members? Phi, Singleton A, Singleton B and B. So set of all subsets of B, this is power set of B, is this. All subsets of B, phi, Singleton A, Singleton B and B itself. I'll take C equals to, for example, set consisting of, let's write anything you can take. I'll take 1, 2, 3, 3 members. I'll list subsets. So what are the subsets here? Phi is a subset of every set. Singleton 1, Singleton 2, then Singleton 3. These are the subset of this. Now I'll take two members. So 1, 2. Now no need to take 2, 1 because 1, 2 is same as 2, 1. So no need to take 2, 1. This is same as 1, 2. Right. So not this. Then 2, 3. Then 1, 3. Two members. Null set, no elements. These are the 3 Singleton sets. Singleton 1, Singleton 2, Singleton 3. Then 1, 2. Then 2, 3. Then 1, 3. And then all 3, that is C. So here power set of C will be all these members 5 and so on this C. So these 8 members will be there, and so on you can do. Now what we notice from this set has how many members? 2 members. So total number of subsets is 2 raised to 2, which is 4. This set has how many members? 3 members. So total number of subsets you can count, which is nothing but the 2 raised to 3, which is 8. Here in this previous example, if you look at here, there is 1 member. So total number of subsets will be 2 raised to 1, which is 2. So in general, this is always true. In general, if a set A has, for example, n elements, then total number of subsets equals to power of 2, that is 2 raised to n. This is very important remark, remember again. If set A has n elements, then the total number of subsets is given by 2 raised to n. For example, if I take, let's take D equals to alpha, beta, gamma and delta. So this has how many members? 4 members. So total subsets of D equals to 2 raised to 4, which is 16. Right? If you want, you can list out phi, then singleton alpha, singleton beta and so on. So this way we have power set. So power set of D, therefore power set of D has 2 raised to 4, which is 16 members. 16 members. Okay, now next is about intervals. You might have studied earlier. So let A and B be 2 real numbers, any 2 numbers. So one is called open interval here. Open interval, which is denoted by this. In a round brackets we write A comma B. This is open interval. It is a special type of set. We define like this: open interval A comma B equals to all real numbers which are between A and B. So it is a special type of set. Open interval A comma B, that is set of all real numbers. Remember, all real numbers between A and B. So if this is real number A, this is real number B, then every number between A and B, which is called open interval AB. This is an infinite set, remember, because there are infinitely many numbers between A and B. So this is open interval AB. For example, I'll write open interval 1 comma 2. So what is that? All x, that is all real numbers between 1 and 2. So here, if this is 1, for example, if this is 2, then all these numbers between 1 and 2. Open interval 1 comma 2. So this is open interval 1 comma 2. Next one, that is closed interval. Closed interval. So it is denoted by this square bracket, closed interval AB. So closed interval AB is nothing but all numbers which are between A and B and including these 2 numbers, 2 endpoints. All numbers between A and B including A and B. So if this is A, this is B, then all numbers between these 2 including A and B. So this is A and this is B. So what is difference between this closed interval and open interval? 2 endpoints are extra in this A and B. The only difference between these 2 is A comma B are excluded here, A and B are included here. So you can see that open interval A comma B would be obviously subset of closed interval A comma B. Why this? Because open interval A comma B means every number between A and B. And closed interval A comma B means what? Every number between A and B including A including B. So there are 2 extra numbers in this, which is A and B. A and B are included here. A and B are excluded here. Same way we can have such interval, open close interval. This means all numbers which are greater than A and less than or equal to B. So this open interval A means A is not included, and close interval B means B is included. And next, closed open. This means all real numbers for which x greater than or equal to A and less than B. That means here square A means A is included but B is not included. Right? So this is called open close interval. This is called open close interval, and this is called the closed open interval. Closed open interval. Closed open interval. So mainly we have these two. One is open interval A comma B. The other one is closed interval A comma B. So universal set here. It is denoted by capital U. That's the standard symbol for universal set, and it means the largest set. It means largest set for a given problem. So now onwards, whenever you use the word universal set, means it is the biggest set or the largest set for a given problem. It may vary from problem to problem. For example, if I have, suppose A equals to this set 1, 2, 3, 4. If I have B equals to, for example, this 3, 4, 6, 7, 10. If I have C equals to this, for example, 0, 2, 4, 6. Then for such a problem, we may take U as universal set as 0, 1, 2 up to 10. This is our universal set. What's the meaning of this? That means all these sets become the subset of this. Each member of each of this set must be present in this. So 0, 2, 4, 6 all are present here. So this is the biggest set for this problem. So this is called the universal set.